In this lecture, I am going to introduce the finite difference method. And we are going to implement the finite difference method different than just about anywhere else you're going to find it. I think what I'm going to show you is maybe slightly strange to learn, but it is a whole lot simpler to implement. And it turns out in the end, the tools you're going to have, you're going to be able to solve almost any differential equation you get in front of you rather than just one. Of course, we're going to focus on Maxwell's equations, but it's a very powerful approach that I'm going to show you. So before we get into that, we need to review some basic linear algebra because we're going to be employing that and we don't want to do anything wrong. Then I want to introduce the concept of finite differences. This is simply a way of approximating continuous derivatives with discrete type functions. Armed with that, then we're going to introduce the finite difference method, and I'll show you how I do things. And I also want to step you through in pretty good detail what I call matrix operators. And it turns out any kind of linear operation like an integral, a derivative, a Fourier transform, there's always a way we can lump that operation into a big ugly square matrix. Okay, the next lecture we'll actually learn about applying this method to solve Maxwell's equations. So here we go. Linear algebra. So matrices and matrix equations. A matrix equation is really representing a whole set of linear algebraic equations. So for example, on the upper left here we have 4 equations, linear algebraic equations. The unknowns in this case are w, x, y, and z. The known coefficients where we should be able to write numbers are the a11, a12, a13, and so on. And then we also have these constants on the right, b1, b2, b3, and b4. Well, it's a bit more compact, and as you'll find out, a whole lot more useful. Rather than write these 4 equations in this straightforward kind of form, we're going to put it in matrix form. We're going to list all of the unknowns in what's called a column vector. So we have w, x, y, and z. All of the coefficients where we have known numbers, we're going to put in a big square matrix. And notice this has just as many rows and columns as the number of rows in this column vector. So we have a 4 by 4 square matrix multiplying a 4 by 1 column vector. And then we lump the unknown constants into this final column vector. So this matrix equation represents this set of 4 equations exactly. But a bit more compact, a bit more simply, and we're going to be able to do some pretty cool things with this. So let's reduce ourselves down to just 3 equations, 3 unknowns for simplicity. So here's our equations, and here's our matrix equation. I'm going to introduce a way of interpreting the meaning of the rows and the meaning of the columns that is technically incorrect. But this will make more sense as we get in and solve Maxwell's equations. So what we're going to say is that this first equation is an equation most closely associated with x. So we'll even call it the equation for x. Even though it contains x, y, and z, and from a pure mathematical perspective has nothing more to do with x than it does y and z. But we're going to call this first equation, or this first row, the equation for x. So the second equation will be the equation for y, and the third equation will be the equation for z. And of course, in order to solve this, we need at least as many equations as we have unknowns. So we have 3 unknowns, we need 3 equations. And so our coefficient matrix, if you will, has to be 3 by 3. Then we're going to look at the columns and interpret the columns as a relation to. So in the first row, that's our equation for x. And this first number is how x is related to x. The second number is how y is related to x. Third number is how z is related to x. So if we jump to some other random point, this is how y is related to z. Now I can't look at the numbers and tell you exactly what that means. I just know that if there's a number there, then those two parameters are related somehow. So the rows is the equation 4, and the columns is the relation 2. This probably doesn't make a whole lot of sense now, but when we jump into next lecture and start solving Maxwell's equations, it definitely will. Okay, so now we're going to adopt a bit more compact notation. So we're back to our 4x4 matrix. Rather than write all these numbers each time, we can write our matrix equation as these bold letters. I tend to use capital letters for big square matrices, and I tend to use lowercase letters for column vectors. So this B is also a column vector. I'm using a lowercase letter. X is a column vector, lowercase letter. A is a big square matrix, big capital letter. Sometimes I deviate from this, but I'm trying to go through my notes and not deviate from that. But my notation is I use a bold letter to represent a matrix, and I make it bold because it's kind of like it's holding more behind it than just a non-bolded letter. Maybe that's kind of weird, but that's what I do. Another thing you'll see in the literature a lot is rather than bold the letters, they'll write the letters in square brackets to remind you that, hey, this is actually some kind of matrix or column vector. And if I ever do this, I'll still try to stick to the convention of capital letters for big square matrices, lowercase letters for column vectors. So given this compact notation, I can write my A as just this big coefficient matrix, X is the column vector of the unknowns, and B is the column vector of the constants on the right hand side. So X and B are column vectors, lowercase, bold. A is a big square matrix, uppercase, and bold. And so that's the notation we'll use throughout this course, in fact. When we manipulate linear or matrix equations, we need special rules. We're not going to do anything real fancy in this class, so perhaps the biggest one is at the top, highlighted in yellow. We cannot reverse the order of operations. So A times B does not equal B times A. And as tempting as we want to do that, we can't do that. And there's some times where if we could do that, it would really simplify things, but unfortunately, we can't. So this is a table summarizing all of the most common matrix algebra identities that we'll need. Most of them are pretty obvious. Some ones I'll point out are down here under matrix inverses and transpose. Maybe it's kind of obvious the inverse of a matrix is the matrix back again. The transpose of a transpose is the matrix back again. And the inverse and transpose operations we can reverse. That's pretty useful. That's pretty cool. Now this is a little bit weird. If we have the product of two matrices, we want to invert that. It turns out it's the product of the inverses of both, but notice now we're reversing them. So it's B inverse times A inverse, whereas over here was A times B. So we can take the inverses of these individually, but we have to reverse the order. So that's very important. And a similar thing happens with the transpose operation. Here's just 3 examples. I'm not going to step you through them now, but you can look at these and try to understand the algebra that's happening here. And so we're manipulating matrix equations and practicing pre-multiplying, post-multiplying, pre-dividing, post-dividing, and stuff like that to simplify expressions. So definitely look this over in your notes. We have 2 special matrices that we'll actually use a lot in this class. So we have a 0 matrix, and I write this as a bold 0, and it's just a matrix with all zeros in it. Now, just by writing a bold 0, that doesn't tell you how big the matrix is. So that's a missing piece of information that hopefully is obvious in the context that's being used. If it's not, you have to find out. In some texts, you'll see people write the 0 matrix, or even the identity matrix we'll get to, and then subscript it with how big it is. And maybe that will be useful, and maybe I should start doing that, but that's not the standard thing to do that. So the 0 matrix is the matrix version of 0. If we multiply any matrix by the 0 matrix, we just get the 0 matrix back again. And we tend to use this where we just want to put in a bunch of zeros. The next matrix we'll talk about is the identity matrix. This is the matrix version of the number 1, but there is not ones throughout the entire matrix. In fact, the entire matrix is all zeros except ones going down just the center diagonal. Anything off the diagonal out here are all zeros. So it's the matrix version of the number 1. So in other words, if I multiply any matrix by the identity matrix, I just get that matrix back again. Also, if I take a matrix and divide it by itself, I get the identity matrix. Okay, now we are ready to step into finite differences and describe what that is. So this is the only finite difference we're going to need for this entire course. I'm going to share a bunch more information with you about finite differences so that you can get a deeper understanding, and you can also go on to do more sophisticated things. But this is it for this course. So we will start off with a continuous function, f of x. This actually contains an infinite amount of information. We can't store that on a computer. So the only thing we can do is store that function value at discrete points. So we might store it here, and another one here, and another one here, and another one here, another one here, another one here. So right away we can see we're missing information when we store things discretely. We can also see the more closely spaced those points are, the better we can resolve that function f. But what you'll discover is the closer those points are spaced, the more points we'll need, and the more computationally intensive your models are going to be. So there's a trade-off. We want the points spaced very far apart so that our codes run fast. We need less points. However, we're also losing accuracy. So in order to get accuracy, we need the points spaced very closely. And there's a sweet spot of where the codes are accurate enough, but still pretty fast. And during the course of this semester, we're going to load you up with rules of thumb for that and how to handle that. So let's start right now. We know the function value at 2 points. Let's say we want to calculate the derivative. The derivative is the slope of the function. So from the definition of slope, rise over run, we can immediately write a way to approximate the derivative right at the center point between these 2 points. So the derivative right at the center point between the points is simply f2 minus f1. This is the rise. So let me go down. So here's the rise. f2 minus f1 is this vertical distance. And then the run, delta x. That's simply that's the spacing between them. So rise over run gives us an approximation for this derivative. So this is a finite difference approximation. We start off with an equation that has this continuous time derivative. However, we are only storing the function at discrete points, and we use finite differences then to calculate derivatives when we only know the function at discrete points. A real important thing to come away with here is that when we calculate the derivative, it exists at the midpoint between f1 and f2. So this is called a central finite difference. So based on that, we can actually define at least 3 different types of finite differences. At the top, we have our backward finite difference, in which case we're going to be sitting on top of f2. We want to know the derivative here, but we're going to use information from behind this. So we're calling it a backward finite difference. We use f1 and f2. Now hopefully it's a little bit intuitive to say, you know what, this isn't the most accurate way to do this. We really should be using information from over here. But sometimes we don't have that information and we're forced to do it like this anyway. So that's called a backward finite difference. Likewise, we can also talk about a forward finite difference, where we're sitting on top of f1 and we want to reach forward, and we're using information from the forward side to estimate the derivative here. Again, this is not the most accurate way to do this. We wish we could use some points over here, but there may be reasons where that's not available. In this class, almost exclusively, we're going to be using central finite differences, which is the most accurate because we're calculating our derivative at the midpoint between 2 points, or at least we're using information from both sides of where we're interested in this derivative. So that's called a central finite difference. To generalize this a little bit, it turns out we can approximate any order derivative as just some linear sum of function values. So if we have a smattering of function values shown in blue, we can approximate the first, second, third order derivative of any intermediate point here just as some weighted sum of these function values. So the difficult part would be determining those weights. What weights would I have to weight all these points by so that when I added them up, I really would estimate accurately whichever derivative I'm interested here. So in fact, any linear operation we can still express as a weighted sum of those function values. Any linear operation, so derivatives, integrals, convolutions, Fourier transforms, anything like that. There's always a way we can come up with a weighted sum. It may not be easy to come up with the weights to do it, but we can always come up with a weighted sum to approximate that linear operation. Now we want to talk about a general purpose procedure for calculating those weights, the coefficients, so that we can take any number of points and come up with how to weight the function value at all those points to estimate either the function or one of its derivatives. So we're going to focus on derivatives and not the other linear operations. We will actually cover some later in the semester, but for right now we're going to focus on derivatives. So the first thing is, let's choose our order accuracy. In other words, how many points do we want to use to estimate our derivative? The more points we use, the more accurately our derivative will become. However, we'll discover later it's going to become more computationally intensive. So what we start off with, we choose the number of points, and then we write a polynomial. So the function value somewhere in the middle of all those points is some unknown coefficient a0 plus a1 times x plus a2 times x squared, and so on. So it's an nth order polynomial. And we have n plus 1 unknowns. We have an a0, an a1, a2, and a sub n. So right away, we know we need one more point in our order of accuracy. The next thing we'll do, we've chosen n so that it'll work with the number of points that we want to retain. So what we'll do is we'll write that polynomial at each of our known points. So we have a known point at x1, x2, to be an x3, so on all the way up to x at n plus 1. And we're going to write the polynomial at each of those points. And if somehow we've chosen our coefficients correctly, a0, a1, a2, so on, then all of these equations have to be satisfied. So in fact, we're going to determine what those coefficients are from those equations. Well, now we know how to write a huge set of equations, linear algebraic equations with those last equations were. We can put them in matrix form. So here's all of our known coefficients in those equations, which in this case are the x values. We have a column vector of our unknowns, which is the a0, a1, a2, all the way through a, and those are the ones we want to determine. So we know the positions of the points, and we also know the function value at those points. So the only unknowns at this point are these coefficients. Well, now we have a simple matrix equation that we can solve for these. So we'll take this big matrix here, we'll call it x, and we'll bring it over to the other side, which means we're going to pre-divide this column vector by x. So we're pre-dividing, or taking the inverse of x and multiplying it by this column vector. Once we've done that, now we have another column vector which contains all of our expressions for a0, a1, a2 through an. Okay, we're going to back up one step real quick, and let's say now we know a0, a1, a2, all the way up to an. Well, what we want to do is somehow write an expression for the function value at some intermediate point or the derivative at some intermediate point. So we're going to go back to the original polynomial, which is this equation f of x. Then we're going to differentiate it. So this next line is the derivative of that. Really what this has done is it's given us a new polynomial, which now, instead of calculating our function value at all those intermediate points, it's going to calculate the derivative at all the intermediate points. If we differentiate this equation again, now we have a new polynomial that'll estimate the second order derivative. And we can keep doing this. We can go on and estimate the third, fourth, fifth, or sixth order derivative. So in this class, we're really only going to work with the first order derivative. Now we still have a problem that isn't a big problem, but can certainly make our lives a lot more convenient. We have x in there, and we sure would like to be able to get rid of x, because then we'll have much simpler equations. So how do we do that? So what we're going to do, we'll take all of our positions, x1, 2, 3, 4, and we're going to translate them across the grid so that our x grid is centered at 0 at the position that we want to calculate the function or one of its derivatives. So there's some position x where we're interested in calculating this finite difference. So we'll call that position x sub fd. We're going to come up with an x1 prime, which is our original x1, minus the position where we want to calculate the finite difference. So we do this for all of our x values, and that has effectively translated our grid so that our x-axis is centered at 0 where we want to estimate the derivative. So the new form of our x matrix is this. We've offset all of the x coordinates to place the 0, x equals 0, at the point where we want to calculate the derivative. So that's all this step did, translate the x-axis. Now if we go back into those polynomial expressions, we've centered our grid at x equals 0, so we set x equals 0 in those equations. So now we can estimate our function, or its first or second order derivative, or so on, with these equations. There's no more x's in it, because we made x equals 0 where we're interested in calculating these things. So these are much simpler, much easier to work with. So we're going to proceed with that. So the best thing to do here is an example. Let's say we have a function and we want to calculate a second order accurate finite difference approximation for the first and second order derivatives. So we want a second order polynomial. So we're going to have an a0, an a1, and an a2 because we have a second order polynomial. We have 3 unknowns. This means we're going to need 3 points in order to calculate those 3 unknowns. So we'll choose arbitrarily 3 points along some arbitrary function, and the same thing over here. Here's our original coordinate system. And for best accuracy, we want to calculate our finite difference right at the center point. So what we want to do is translate our coordinates to place 0 right at x2. So over here now is our translated coordinates. Now we have 0 over at x2. The first point then is just simply minus delta, where delta is the spacing. The third point is at positive delta. So it's a simplified grid in a way, but it is, the most important thing is that it's centered where we want to calculate our finite difference. Next step is to calculate our x matrix, and we're calculating the x matrix in the translated coordinate system. So we end up here. Then we need to invert it. So here's our x matrix, and we invert it. And you're welcome to use any kind of symbolic math toolbox if I ever ask you to do this, but I don't actually think that I am. But I use a symbolic toolbox to do this. It's not too bad to do it by hand either. Okay, so now we're going to pre-divide our f column vector by x, or we're multiplying f by the inverse of x. When we do that, we get a column vector which gives us our 3 polynomial coefficients. So we work through that, and here's the answer of our polynomial coefficients. So notice this is a function of our grid parameters, which was in x, and also the f's, which was in this column vector. So now we have expressions for our three polynomial coefficients. Now we can plug these back into our expressions that estimate the function or one of its derivatives. So remember, if we wanted to interpolate the function at x2, that was just a naught. Well, from the previous slide, that was just f2. Well, that makes sense. We're interpolating the function where we actually happen to know it, and so it's just f2. So that's great. If it turned out to be something different, we'd know there was a mistake. So our first order derivative at x2 is simply going to be just a1. Well, we had a1 from the previous slide. So now we actually have an expression to estimate our first order derivative at x2. Likewise, the second order derivative at x2 was 2 times a2. So inside the square brackets was our expression for a2 that we found on the previous slide, but we need to multiply it by 2. And that came out of taking the derivatives of the polynomials. That's why that 2 appeared there. Okay, so grabbing these, here are now our three expressions for our finite differences. One more example. We're going to try the next order of accuracy where we actually want to reach out over 4 different points and calculate our derivatives, functions and derivatives. So we need a third order polynomial. Our third order polynomial is going to have 4 polynomial coefficients, so we need 4 points. So we're going to distribute 4 points along an arbitrary function. We're going to give it a spacing delta, but they're at position x1, x2, x3, and x4. And we're going to say that we want to calculate our finite difference at the midpoint between x2 and x3. So we want to calculate our function or one of its derivatives right here where I have the red dot. Okay, what's the first thing to do? Translate the coordinates so that 0 is right between x2 and x3. So here's our translated coordinate system. Now, if we have 0 right here at the midpoint, and the spacing between the points is delta, then the position of this first point is simply 1/2 delta, because we just moved from where it's 0 over half a delta. Then this next point, or the last point, is at 1.5 delta. The second point is at negative 0.5 delta, and the first point is at negative 1.5 delta. So that is our translated coordinate system. So now we calculate our x matrix, where we bring in all the translated coordinates and we fill them in here. So that's what our big ugly x matrix looks like. Then we invert it. Again, I used a symbolic toolbox to do this, but here's our inverse matrix. Now we have to multiply this inverse matrix by that column vector f in order to calculate the polynomial coefficients. So here we are. We've skipped a few steps, not that many though. So in the next step, we had our polynomial. We would have had our polynomial coefficients, but you can see what those are here. A naught is this expression, so that is our inverse x matrix times the column vector of f's. Our a1 is simply that, and our a2 coefficient is what is inside the square brackets. Okay, so to estimate our function value at the midpoint between points 2 and 3, I just put 2.5 here to convey that, it's just a naught. And so that's our expression for interpolating the function f at the midpoint. We took the derivative of the polynomial and found when we set x equal to 0, it's just a1 to estimate the first order derivative at the midpoint between points 2 and 3. Here's our expression for that. We took the next derivative of the polynomial to estimate the second order derivative, and in this case it was 2 times a2. The 2 arose due to the derivative operation when we took the derivative of this polynomial to get down to here. So the 2 has to multiply the polynomial coefficient a2. Well, we pull all these together, and here are now our 3 expressions. The first one to interpolate the function value at the midpoint between 2 and 3. This next one to calculate the first order derivative at the midpoint, and to calculate the second order derivative at the midpoint. You may also see in some textbooks these things called finite difference atoms, and I've drawn the atoms for some of the things that we just calculated. There's also the atom for the Laplacian at the bottom here. I tend not to use those because the way I do finite differences is we do one step where we incorporate finite differences in what we'll call a derivative operator, but from that point forward we don't ever touch finite differences, so we don't need these pictures as extensively as other people that I think implement finite difference method a bit more tediously. But I want you to see it and know what people are talking about. It's just a graphical representation of what we've just talked about. Okay, on to the actual finite difference method. So the finite difference method, the goal of it is to start with some arbitrary differential equation and end up with a big matrix equation that we can solve and calculate all of our unknowns at discrete points. That's the goal of the finite difference method. It's just a way of discretizing a differential equation, casting it into matrix form, and solving it. So we can take two paths. The typical path is shown on the left. Step one is to take our differential equation, approximate all the derivatives with finite differences, and that can be a pretty tedious task. Then we have a lot of algebra to do. We have to expand this, we have to collect all the coefficients multiplying the common terms of f, and then from there we can take that big ugly equation, which can be very confusing, and we can cast it into a matrix form. And that step is very difficult, very tedious, and prone to a lot of mistakes. And also, once you've done it, what you're left with is only valid for that one differential equation. But anyway, we certainly can get here, and this is the way pretty much the entire world does it. Once you're here, then you can solve it pretty easily. What I'm going to show you how to do is to go from the differential equation immediately, in an effortless step, write it in matrix form. Then from here we can cast it into the form that we had over here, some linear operation multiplying your unknowns equaling a source condition. So in this case, L is going to be D minus A. So imagine factoring out the F up here, and it's D minus A factored out. So we'll just simply calculate L equals D minus A, and then we can solve it very easily. So this is a hugely more simple task. The tedious step, maybe you'd think, would be going from here to here, but literally there's going to be nothing to that. We're going to have a function, and you'll hand it the size of your grid and the grid spacing, and it's going to calculate these matrices for you. This will be a very simple diagonal matrix probably. So that's one function call in MATLAB to do that. Another function call, or another line of code, L, to calculate this, and then a third one to solve the matrix equation. So in 3 lines of code, we can traverse this whole other side. Over here, that's definitely not as easy. So that's the finite difference method and how we're going to do it. So back to the concept again. Here we're over at the left. We have some function in 2 dimensions, and like before, this has an infinite amount of information. We can't store an infinite amount of information on a computer. So instead, we'll take whatever area of space describes our problem, and we'll divide it into a bunch of cells. The more cells we use, the more accurately we can resolve that function, but certainly the longer it's going to take for the computer to solve. So there's a trade-off of how big we make the cells, and we'll learn rules of thumbs on how to do that. But the next thing is, within a cell, there's still a continuously varying function. There's still an infinite amount of information even in the cells. So we're going to pick somewhere within that cell a point, and that's where we're going to store the function value. So everywhere else, we no longer know the function value. So now we're missing information. So if you want to envision a grid where we're going to be implementing finite differences, this picture on the right is that. So this is what is representing our original function. We're missing information, but now we can store this on a computer. And we're ready to implement the finite difference method on it. So we can look at a single cell, and we'll call that a unit cell of our grid, and it has some spacing in the x direction, we'll call that delta x, and some size in the y direction, we'll call that delta y, but there's still an infinite amount of information here. We're going to store our function value only at one point within that cell. Now what you'll see later, we can choose where that is. At this point, it makes intuitive sense to place it at the middle, but we could also maybe place it at the origin or any other point. So we're going to call delta x and delta y our grid resolution parameters. The smaller those numbers, the higher the resolution of our grid, the more accurate our answer is going to be. The pictures of the fields are going to look better, but our models are going to take a lot longer to run because there's just more calculations that have to happen. Okay. Regardless of the number of dimensions that we're modeling, 1 dimension, 2 dimension, 3 dimension, even 10 dimensions, we can always list all of our unknowns in a single file line. Think of how memory is stored on a computer. No matter how many dimensions your arrays might have in your computer code, in memory it is stored serially anyway. So for a one-dimensional grid, F1 through F5, it makes sense. We'll just store them in a column vector, F1 through F5. For a two-dimensional grid, what we do is we raster through the grid. Maybe we go this way first. F1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we rastered through this two-dimensional space, and we list them all in a single file line. So if we had a three-dimensional array, we'd have to raster through it. But there's always a way we could list all of the unknowns throughout that grid in a one-dimensional column vector. In this case, since we're just saying the function f, we're going to call that column vector a bold f. Another way you can visualize this, so imagine we have a grid and we kind of string some kind of rope through this, and we grab it either side and pull it tight, and then all of a sudden here is our column vector. Now pulling the string, MATLAB has a command to do that. Let's say we have f, which would be a two-dimensional array. If we say in just one parenthesis a semicolon, I'm sorry, that's a colon, we'll come out with f, which will be a column vector. And we can also go from the column vector back to the 2D array using the reshape command. We'll give it the 1D array and tell it this is really going to become a 2D array that's nx wide and ny tall. And then we get f back again, that's a 2D array. So MATLAB makes it real easy for us to go back and forth between multi-dimensional arrays and column vectors. So this is going to be a summary of the conventional finite difference method. Now there are some rules to this that will apply to us as well. So we're going to choose a arbitrary second order differential equation, could represent anything. So that's our starting point. We're going to call this our governing equation. That's the one equation that explains everything we need to know about our problem. The next thing we do is approximate each derivative with a finite difference. So before we had derived the approximation for a second order derivative and a first order derivative, and so we plug in our approximation for the second order derivative and plug in our approximation for a first order derivative. And this parameter k is an integer, and that's representing the point along our grid. So it'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to however many points you have. Now, a really, really important rule that we can see at this point, we have to look at all of the terms in our finite difference equation and make sure they all exist at the same point. So this is where the forward, backward, central finite difference thing comes in. They all define the derivative at different points. So we need to make sure that this first term calculates a derivative at k. This second term calculates a derivative at k. This third term calculates a quantity at k. And this last term over here calculates a quantity at k. So all these quantities now, if you look, actually exist at the point k. That is a valid finite difference equation. If that weren't the case, then we would probably have an unstable code and we would run into problems at strange points. Sometimes it might even work a little bit. And that's the worst case because it can look like it's working and then suddenly not. So anytime you write a finite difference equation, every term, whatever quantities that representing, needs to exist at the same point. The next step, which can be very tedious, we have, for example, an f at k minus 1 and another f at k minus 1. So we need to expand this equation and collect all the coefficients on the common terms of f. So if we work through all that algebra, blah, 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 here's the expanded equation. We collect all the common terms, and we end up here. So there's a lot of algebra in this step, and in fact, this is a pretty easy equation. If we were solving Maxwell's equations this way, we'd actually have 8 equations that we'd have to do this to, and we would start to go insane very quickly. But anyway, here we are. So here's our equation. We collected all the coefficients multiplying these f terms, which are our unknowns. And this c is some kind of source condition. Now, I just rewrote that same equation, but I color-coded these coefficients. What we're going to do is we're going to jump from this into matrix form. We're going to list all of our unknowns. These are all the f at k, k minus 1, whatever, at every point in our grid. Here's all the c's, those unknown constants, which, as we'll learn, is a source later on in this column vector. But these coefficients go into to populate this big, ugly square matrix. And it turns out this first term, which is coupling to a previous k value, think of this as the equation. We'll go down to some middle point. Think of this as the equation for k. This, as it turns out, will be the column or relation to k. So this center term in blue is the coefficient describing how f at k is related to f at k. So that's what we see here. Then we come over. This is how f of k is related to f of k minus 1. And that's where this term comes in. And likewise, the red describes how f of k is related to f of k plus 1. And that comes in here. So we literally just read off these numbers and we populate our global matrix. And this is not that easy of a step either, but sometimes not too bad. For this little differential equation, it's probably the easiest. It really only gets uglier from here. Well, now we have our matrix equation. We'll call this big ugly square matrix L. I use L for just some arbitrary linear differential equation. So we'll call that matrix L. We have this column vector of our unknowns F, and a column vector of these unknown constants C, which we'll learn later is a source. So I like to write it this way with the bold letters. Well, now we can actually solve it for F. We pre-multiply both sides by L inverse. So I'm going to have an L inverse times L. That'll give me the identity matrix, and it just disappears. We're left with just F. And then an L inverse times C on the right. So that's how we'll solve for our unknown function f. So the differential equation was describing the function f. The physics of the differential equation get lumped into L, and the source condition or the excitation gets lumped into C. So that's it. That's the conventional method. Our method, we're going to start with our differential equation, and we can just term by term write everything as a matrix. We immediately know that f is going to be a column vector, so we can immediately write that. This is a linear operation. There's going to be a big square matrix that will calculate such that if we multiplied this big square matrix times f, we would get another column vector that if we plotted, we would see the second order derivative. This is another linear operation operating on f. F is our column vector of unknowns. That's an operation operating on f. It becomes a big square matrix such that if we multiplied this big square matrix by the column vector f, we would get another column vector that if we plotted, we would see the first order derivative of f. We have another thing out here. It's another function operating on f, so it becomes another square matrix that operates on f. Over here, f is a column vector. And B is now operating on F, so it becomes a big square matrix. This is our source condition or excitation. It's going to be a column vector of a bunch of unknown constants. So just knowing that, we don't know what goes into B or D or A yet, but just knowing this, we can immediately on paper go from the differential equation to the matrix form. And what we'll discover by doing it this way is that these matrices are very simple and easy to construct. And so that'll be some real simple MATLAB code to create these. And once we have that code to create these, on paper we can just jump straight from the differential equation to the matrix form. We can factor out the F, so we're left with all the things operating on F, and that gets lumped into L. And in fact, this is the same L that we would have derived before, but this is a whole lot less work, as you'll see. And then we solve the matrix equation, and we'll get the same exact answer as before. The previous way we did this, the conventional finite difference method, gives you the same answer. It's correct and valid, but in my opinion, this is a lot simpler, because if we look at this, we don't see any finite differences in this. We're actually implementing the finite difference method without ever touching a finite difference. And in fact, we can handle any number of different differential equations very easily and very quickly this way. Our next section is matrix operators. So what is a matrix operator? Let's look at a column vector of our known function. So we have some function and all the points where we're storing the values. Now we want to do some linear operation to that function. In this case, we're going to be doing derivatives. So the question is, what big square matrix would I multiply this column vector by so that I get another column vector that if I plotted it, I would have the derivative of this function. So I could plot these and see the function, plot the new column vector I would get from the product of these two, and then see the derivative, or in fact see whatever linear operation I'm interested in. But anyway, this big square matrix that performs the linear operation, we are going to call the matrix operator for that linear operation. It turns out anything that is linear, any kind of linear operation we can perform on a function, there's always a way we can wrap that into a big square matrix. So that includes Fourier transforms, point-by-point multiplications, convolutions, integrations, Laplace transforms, anything you can think of. There's always a way I can construct a square matrix that we can multiply a column vector by so that we get a new column vector that if you plotted it, that would be the function. It would look like the function with that operation performed on it. So that's a matrix operator. The first and simplest of the matrix operator is a point-by-point multiplication. So we're going to store our function in a column vector. That'll be the f's. This is an operation being performed onto f. We are doing a point-by-point multiplication of this function b. So the question is, what would this big square matrix look like? What would it look like so that we would get this column vector that has the point-by-point multiplication? It's b1 times f1, b2 times f2, b3 times f3. So what needs to go in this big matrix so that we would get this as a result? When we figure that out, we will have the big square matrix, or we have our matrix operator. So here's the answer. It turns out it's a diagonal matrix where the values of b, b1, 2, 3, 4, 5, and 6, go along the diagonal. So if you do your row column operations and multiply this column vector, you'll see that you definitely do get this. So point-by-point multiplications are performed by diagonal matrices, matrices that are zero everywhere except numbers going down the diagonal. So in this case, our diagonal matrix we call capital B. That is our matrix operator for a point-by-point multiplication with B. A little more difficult now. What would this big square matrix look like to perform a derivative operation? So we have our function stored in a column vector, only 6 points here. And we want to know what gets in here, such that if we take this big square matrix, multiply by this column vector, we will get another column vector, which is its derivative. So what I like to do is figure out the answer first, and then work backward to fill this in. So recall our finite difference approximation. Let's take the second point. How do we calculate the derivative, or the slope, at point f2? It's going to be f3 minus f1 divided by the spacing between them. And in this case, the spacing between them is going to be 2 times delta x, because we've actually spanned 2 spaces now. And we can write that same equation for f3, in which case it's going to be f4 minus f2 divided by the spacing. And I can go through all of these and write a finite difference approximation to calculate that derivative at each point. Now we run into 2 problems. When we calculate the slope at f1, at the edge of our grid, or the boundary, we need f2 minus some f0 out here that doesn't exist. So how do we handle that? And also down here, we need an f7, which doesn't exist, minus f5. So we have another problem here, and we don't know how to handle that yet. So for now, we are going to assume that f0 and f7 are just 0. So we're just going to drop them out and ignore them for right now. In which case, this is how we would fill in this big matrix operator. Now each of these ones is actually being divided by 2 over delta x, but it's, I think, clearer to bring the 1 over 2 delta x to the outside and just leave negative 1s and 1s going down the 2 diagonals. So this big square matrix, multiplying our function, will give us another column vector, so that if you plotted it, you would see the derivative of this original function. Notice how easy this is to construct. We just insert 2 diagonals in our matrix and then divide the whole thing by 2 delta x, and we have our matrix operator. That's the beauty of this. We have a very big, complex matrix that we need to construct, but we're going to construct it from little small matrices that are very easy to construct. These derivative operators, point-by-point multiplications, or anything else that would pop up. And MATLAB's very good at placing and extracting diagonals from matrices, so we can insert those 2 diagonals with either 1 command or 2 commands. I like to break it up into 2 for simplicity. So it's literally 2 lines of MATLAB code will construct this matrix operator that will perform derivatives for you. Okay, what about a second order derivative? Again, we will store our function in a column vector. We need to answer the question, what's going to go in this big ugly square matrix, that if we multiplied it by this column vector, we would get another column vector, which is the second order derivative of f. So if we plotted it, we would see the second order derivative. So we go back to our finite difference approximation for the second order derivative, and let's be right at the f2 point. We want to calculate the derivative here. What we see is that it's f3 minus 2 times f2 plus f1 divided by delta x squared. We derived that earlier. And I could write a similar finite difference expression for each point. Again, we run into the trouble where we're writing the finite difference expression and we need a value from outside. We need what would be an f0, and down here we need what would be an f7. So for now, we're just going to ignore this and set those to 0. And if we do that, here's how we would fill in that big square matrix. We have negative 2's running down the diagonal, and then on the upper and lower diagonal, we just have positive 1's. And then, of course, we divide the whole thing by delta x squared. So this big, ugly matrix is the matrix operator for a second order derivative. So if we have some function here and we plotted it, and then we plotted whatever ends up here, we would see the second order derivative of the function. So what about 2-dimensional grids? And it gets a lot more a lot more tedious, I would say, to write the derivative operators for two-dimensional grids. And we could also talk about doing these on three-dimensional grids. We're not going to do that in this class, but we will do two-dimensional grids. So we're going to lay our two-dimensional grid out this way. So we have x running from left to right and y running from top to bottom. And we have some function that's now a function of x and y. It's a two-dimensional function. And we want to take the second order derivative in the x direction. Again, we have 9 points. We raster through these and we list them all in a single file array, a one-dimensional array, a column vector. So we have 9 values here. And we need to fill in this big ugly square matrix such that we would get the second order derivative in the x direction over here. So let's look at a few points. If we're sitting at f1, the way we would calculate the second order derivative, we would say f2 minus 2 times f1 plus some f that doesn't exist out here over delta x squared. And that's exactly what we have here. But we don't know how to handle this because we don't know what's outside of our grid. Let's go to the second point. Now we have an f3 minus 2 times f2 plus an f1 all over delta x squared. No problems. We have everything we need there. Now we go down to f3. We need a field value from out here, which does not exist, minus 2 times f3 plus an f2 all over delta x squared. So here's our finite difference approximation and this function value from outside the grid that we don't know how to handle yet. Well, so this process repeats. I could go through the same argument for the remaining 6 points, and I could fill in my finite difference approximations this way, noting that every time we have this subscript of a question mark, that's a function value from outside the grid that we don't know what to do with. So for now, we're just going to drop these off and pretend that they're 0. When we do that, this is how we would fill in that big ugly square matrix, so that if we multiplied it by this, we would see our second order derivative. Now this is a column vector, so after you've calculated the derivative, we would need to reshape it back to a two-dimensional grid and then plot it to see the derivative. The best way to do this is to draw a 3x3 grid and do another 4x4 grid and just work through the equations one at a time. And you'll get the pattern, you'll get what's happening, and then writing your code will be a lot easier. Okay, now we need the y direction. Turns out this is actually a little bit simpler. So let's start off at f1. So our derivative in this case will be f4 minus 2 times f1 plus whatever is out here, but there is nothing on the outside, so we don't know how to handle that, all over delta y squared. So that's what we see at f4 minus a 2f1 plus this function value from outside the grid that doesn't exist, divided by delta y squared. And it's the same story for all 3 of these points. They're all trying to reference function values from the outside. So all these function values that from the outside appear here that we don't know how to handle. For now, we're just going to drop them out of the equations, pretend that they're 0. So now we have the second row of equations. So let's say we're sitting at f4. The finite difference in the y direction is going to be f7 minus 2 times f4 plus f1, all divided by delta y. And so that's exactly what we have, f7 minus 2f4 plus f1 all over delta y squared. And in fact, there's no problems writing the finite difference equations for anything in this second row. So now we get down to the third row, and we're sitting on top of f7. The second order derivative will be some f down here, which doesn't exist, minus 2 times f7 plus f4, all divided by delta y squared. So here we have that function value from outside the grid that we don't know how to handle, minus 2 times f7 plus f4 divided by delta y squared. And we're going to have the same problem no matter which one of these points we're writing finite difference expressions for. We need function values down here that are outside of the grid. Anyway, we fill in our answer. This is what we have to get, and now that makes it simple to fill in the numbers over here. This is what it would take. This is our matrix operator for a second order derivative in the y direction. So now we need to look at this problem at the edge of the grid a little bit more technically. This is what's called a numerical boundary condition. Remember before we talked about physical boundary conditions. This is the whole transverse component of the field values are continuous across the interface. That's a physics-based boundary condition. A numerical boundary condition is when we're at the edge of a grid, we have a finite difference equation or any equation, but it needs a value from outside the grid, which is impossible. We don't store those. How do you handle that? Well, what we've done so far would actually be called a Dirichlet boundary condition. We assume that all function values outside the grid are 0. Now, if we do this, we are actually forcing the fields outside the grid to be 0. So if the physical reality of what you're modeling, if that is not the case, this is not a good boundary condition to use. But it would be a good boundary condition, for example, let's say we're modeling the field around the transmission line or inside a waveguide. The field's confined, and we can make our grid encompass the waveguide in a whole extra space so that all the fields are inside the grid and not touching the edges. And this is a great boundary condition to use in that circumstance. It's also the simplest, and it's called a Dirichlet boundary condition. So let's look at these matrices. These are on 2D grids, and they are performing second order derivatives in the x and y directions separately. Some things I want to point out. While they're a little bit weird to construct, or a little bit weird to derive, they're actually very simple to construct. Let's look at the y derivative. This is exactly just 3 diagonals. There's the center diagonal always have -2's, and we have a diagonal with 1's and a lower diagonal with 1's. The only trick is figuring out where the diagonals go. The -2's always go down the center, but we have to figure out where these 1's go, and that depends on the width of your grid. The x derivative is a little bit more involved. The numbers are always going to go down the center diagonals, so we still have -2's down the center. But notice the upper and lower diagonals. They're almost all 1's, except every once in a while we have 0's put in there. And that's because the boundary conditions for the x-axis just occur at different spots than the boundary conditions did for the y-axis. So what I like to do is, for the x derivatives, is just go in and place blindly 3 diagonals. -2's down the centers, positive 1's in the upper and lower diagonals. Then I go back and correct just in those places where we had to handle the boundary condition at the x-axis boundaries. And that I found to be the simplest and quickest way to do it. So let's look at this. Why do we need separate matrix operators for first and second order derivatives? We know from calculus, if we just multiply 2 first order derivatives together, we get a second order derivative, and that would hold for x or y. So why can't we just calculate a single first order derivative, multiply it by itself, and get a second order derivative? Can we do that? So the answer is yes and no. If we did that, this is what we would get. We would get the correct matrix. However, we're not efficiently using our grid resolution. Notice this diagonal of 1's is over 1 more space than it would be if we just constructed this from the second order finite difference approximation. What this means is we're reaching out farther into the grid to calculate the second order derivative. So we aren't using the full resolution of our grid as effectively as we could. The derivative operator here is not as accurate. We're not using the information from these points. If we're calculating derivatives, we want to look very locally. We don't want to reach way out into the grid. Now this will still work. It still calculates a second order derivative. It's just you're going to take a very large hit in accuracy. Whereas building this one directly, there's no problems. So at this stage, we actually need separate derivative operators for first, second, third, and fourth order derivatives. You'll notice when we get into Maxwell's equations, we're going to change the story a little bit, and it'll turn out we only need the first order derivatives. But we're going to do something a little bit different when we get to that point. But for now, we can't do that. We really need different first order, second, and if we needed them, third, fourth, fifth derivative operators. So the rest of these slides, I don't need to step you through. These are examples because one of the homeworks coming up is you're going to write a function where you tell it the size, so big NX, big NY, and the resolution, dx, dy, and it'll calculate these derivative operators for you. And you can use these examples to help benchmark to make sure you're getting the correct answers. So here's an example for a 5 by 5 two-dimensional grid, and it is a first order derivative in the x direction, second order derivative in the x direction for that same 5 by 5 grid. Notice it's 3 diagonals, but there's zeros placed in there, and that corrects the numerical boundary conditions at the x-axis boundaries. Same grid, first order derivative in the y direction. We don't have to go back and correct for boundary conditions just because of the locations where they occur. So we just place 2 diagonals and we are done. Second order derivative in y. Here we're placing 3 diagonals, but again, we don't have to go back and correct boundary conditions. That's just due to where the boundary conditions are. Now, if you wanted to go to a 3-dimensional grid, we're not going to do that in this class, but here is what the matrix operators would look like. So first order derivative in x, second order derivative in x, first order derivative in y, second order derivative in y. Now since we have a 3-dimensional grid, we can take derivatives in the z direction, and that's what comes next. Here's a first order derivative in z, second order derivative in z. Now one thing I'll point out, these matrices are zeros almost everywhere except in those 3 diagonals. And at some point we're going to talk about what's called sparse matrices. Sparse matrices only bother to store the non-zero elements. And even these matrices, a 4 by 4 by 4 grid, that's really tiny and unusable. More realistically, a 3-dimensional grid would be 40 by 40 by 200. These matrices get absolutely enormous, but they're mostly zeros. So if we store them as sparse matrices, they really only take up a few kilobytes. If we stored all those zeros as double floating point numbers, we would run out of memory and our computer would melt and you'd form a black hole on your desk. I think that's it for this lecture.